In this video, we'll be going up the bottom-up array approach of unique binary search trees. Let's go over the thought process. Let's convert the top-down memorization approach to a bottom-up approach. Now, where do we start? In the memorization approach, we have cached the number of nodes n with the number of binary search trees that we can generate. This means we can create an array, trees, to keep track of the number of binary search trees for all possible values of n. Now we'll ask ourselves, what are the default values inside the trees array? When n is equal to 0 or 1, then we can generate one possible tree. So we can say then the number of BST is equal to 1. Let's go over the pseudocode. So we're going to create an array, trees, to keep track of the number of trees for all possible values of n. Then we're going to iterate through from 0 to n, denoted as I. If I is equal to 0 or 1, this means we are hitting our default values here. Then the number of BSTs is equal to 1. So we're going to set trees of I to 1. Then we can continue to next iteration. Now we're going to iterate through from 1 to I, denoted as j. These will be the roots nodes, and now we want to generate the left subtrees and the right subtrees. So we're going to increment trees I by the number of trees on the left, so trees j minus 1, and the number of trees on the right, so times by trees I minus j. Then we can return trees of n, basically the number of binary search trees that we can generate with n nodes. Let's go over the time and space complexities. So for the time complexity is O of n, where n is the input value. This is because of our nested for loops. And our space complexity is O of n, where n is the input value and is the trees array. Let's go over the code. So we're going to create our trees array first to keep track of the number of trees for all possible values of n. It's going to be size n plus 1 because we want it to be 0 to n. Then we're going to iterate through the indices from 0 to n. I currently keeps track of the current number of nodes available. So if I is equal to 0 or I is equal to 1, then the number of trees is equal to 1. Then we can continue in the next iteration. Then we want to iterate through all the possible roots. We want to increment the current number of trees by the number of left subtrees times by the number of right subtrees. So trees of I incremented by the number of trees on the left times the number of right subtrees. I minus j. It's j minus I and I minus j. Then we can return trees of n, which is the total number of trees or binary search trees that we can create with n nodes. Let me know if you have any questions in the comment section below.